Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us into the quiet world of rain, where we will explore how raindrops form, why storms move across the sky, and how rainfall shapes rivers, forests, cities, and stone. The story of rain begins inside Earth's slow and steady water cycle. Water leaves oceans, lakes, rivers, soil, and leaves as vapor, lifted by warmth from the sun. This vapor does not vanish. It becomes part of the air, moving quietly with winds across land and sea. When the air rises and cools, the vapor can change back into tiny liquid droplets or ice crystals inside clouds. In time, some of that water returns to the ground as rain. The same water may later sink into soil, feed a stream, enter a river, or flow back toward the ocean. This cycle has no true beginning or end. It is a continuous exchange between sky, land, and water, and rain is one of its most visible moments. Each shower is a brief, familiar sign of a much larger movement. High in the air, raindrops usually begin around tiny floating particles. These particles can be bits of dust, sea salt, smoke, pollen, or other small materials carried by wind. Water vapor usually needs a surface to gather on, because cloud droplets form much more easily around particles in the air. The particles that help this happen are called condensation nuclei, which simply means small centers where condensation can begin. Around them, invisible vapor becomes visible as a mist of droplets. A cloud is made from vast numbers of these tiny droplets or ice crystals, each one far too small to fall as rain at first. The cloud looks soft and weightless from the ground, but inside it is a quiet collection of water forming around specks almost too small to imagine. Before a cloud can release rain, its droplets have to grow much larger. At first, the droplets inside a warm cloud are so small that gentle rising air can hold them up. They drift, collide, and sometimes merge, making larger drops through a process called collision and coalescence. This happens especially well in clouds over warm oceans, where moist air supplies plenty of water. A slightly larger droplet falls a little faster than the smaller ones around it, so it can catch them on the way down. Each joining adds a little more weight. Over time, the drop becomes heavy enough to overcome the rising currents inside the cloud. What began as a suspended mist becomes a falling raindrop, released from the cloud by the simple pull of gravity. Growth in a cloud can be quiet, but its result is visible everywhere below. In many cooler clouds, rain begins as ice, even when it reaches the ground as water. High in the atmosphere, temperatures often drop below freezing, and clouds may contain both tiny liquid droplets and ice crystals. In this setting, water vapor tends to gather more easily on the ice. The crystals grow while nearby droplets become smaller, feeding the process. This is often called the Bergeron process, named after a scientist who helped explain it. As the ice crystals become heavier, they fall through the cloud. If the air below is warm enough, they melt before reaching the ground, becoming ordinary rain. A gentle shower at the surface may therefore have begun its fall as delicate ice far above the landscape. The path from cloud to earth can include more changes than the eye can see. A falling raindrop is not shaped like the teardrop used in drawings. Small drops are close to round, because surface tension pulls the water into a compact shape. As drops grow larger, air pushes up against their lower side, while gravity pulls them downward. This pressure flattens the bottom, making a larger raindrop look more like a tiny hamburger bun than a falling tear. If a drop grows too large, the air pressing against it can make it wobble and break apart into smaller drops. This is why raindrops have a natural size limit. The familiar teardrop shape is useful in drawings, but real rain has softer, rounder forms shaped by a quiet balance between water, air, and motion. Each falling drop is being gently sculpted during its descent through open air. As a raindrop falls, it eventually reaches a steady speed called terminal velocity. At first, gravity pulls a raindrop downward and it speeds up. As it falls faster, air resistance grows stronger, pushing upward against the drop. Eventually, the downward pull of gravity and the upward push of the air balance each other. At that point, the drop keeps falling at a roughly steady speed, rather than accelerating without limit. Small drops fall slowly, while larger drops fall faster, though even they are slowed by the air around them. This balance protects the ground from the full force a falling object might otherwise have. Rain can feel sharp in a storm, but each drop is still moving through a cushion of atmosphere that gently controls its descent. The air is an unseen part of every rainfall. Not every drop that leaves a cloud reaches the ground. This kind of rainfall is called virga, and it appears as pale streaks or curtains hanging beneath a cloud. The drops begin their descent normally, but they pass through a layer of dry air below. As they fall, the water evaporates, changing back into vapor before it can touch the surface. From a distance, virga can make the sky look as if rain is trailing downward and fading away in mid-air. It is common in dry regions where the lower atmosphere can absorb falling moisture quickly. Virga is a reminder that rain is not only about clouds above, but also about the air it must travel through on the way down. Sometimes the journey ends before the earth is reached. The familiar smell after rain often comes from the ground, not from the rain itself. One important source is a compound called geosmin, made by certain soil-dwelling bacteria. During dry weather, traces of this earthy scent can build up in the soil. When raindrops strike the ground, they can release tiny bubbles and aerosols that lift the scent into the air. Oils from plants and minerals on dry surfaces may add to the smell as well. This fresh, earthy fragrance is often called petrichor. It can be especially noticeable when rain follows a long dry spell, because the land has had time to gather these quiet scents. Rain arrives from the clouds, but part of its character rises from the soil below. The scent makes rainfall feel connected to the place where it lands. The sound we call rain is made by millions of tiny impacts. Each drop creates a small event when it lands, whether it strikes a leaf, roof, window, puddle, lake, or patch of soil. A light shower makes softer, scattered sounds because the drops are smaller and fewer. Heavier rain creates a fuller sound as many drops land close together. The surface matters too. Water on broad leaves may sound soft and rounded, while water on metal or glass can sound sharper and brighter. In puddles, drops create little splashes and air bubbles that add their own tones. A steady shower can also mask distant traffic, footsteps, voices, or animal calls, gently changing the listening distance around a person. The result is not one sound, but a layered pattern of countless small touches. The same shower can sound different in a forest, a garden, or a city street. Drizzle is made of very small drops falling close together. These drops are usually less than 0.5 millimeter wide, so they descend slowly and can seem to float through the air. Drizzle often comes from low clouds called stratus clouds, which spread in grey sheets rather than rising into tall storm towers. Because the drops are so fine, drizzle may dampen clothing, streets, and leaves without creating the clear tapping sound of heavier rain. It can reduce visibility and make a landscape feel softly blurred. Though gentle, drizzle can last for hours when moist air remains trapped near the ground. It shows that rain does not always arrive with drama. Sometimes it settles over a place in a thin, quiet veil. Its small drops can still give the ground a steady share of water. To measure a shower, meteorologists usually record how deep the water would be if it stayed where it fell. A rain gauge catches falling water in an open container, and the amount is recorded as a depth, often in millimeters or inches. 10 millimeters of rain means the water would cover a flat surface to a depth of 1 centimeter, or a little less than half an inch, if none of it ran off, soaked in, or evaporated. This simple idea makes it possible to compare rain in different places. A brief downpour and a long, gentle shower can produce the same total amount. The gauge turns a passing event into a clear record, preserving the quiet fact of how much water the sky returned to the ground. A small number can describe a whole cloudy afternoon. Along mountain slopes, moist air can be lifted until it cools into cloud and rain. When wind pushes air toward a mountain range, the air cannot pass straight through the rock, so it is lifted upward along the slope. As the air rises, it expands and cools. Cooler air can hold less water vapor, so clouds form, and rain may fall on the windward side of the mountains. This is called orographic rain, from a word connected with mountains. Many green mountain slopes and wet coastal ranges owe much of their rainfall to this lifting process. The mountain does not create water from nothing. It simply changes the path of moving air, guiding moisture upward until it becomes visible as cloud and then falls as rain. Stone, wind, and vapor work together in a slow meeting place. On the far side of some mountains, dry rain shadows can form. After moist air rises and drops rain on the windward slope, it often crosses the mountain crest with less water vapor than before. As the air descends the opposite side, it warms and becomes better able to hold moisture, so clouds are less likely to form. The land below may receive much less rain than areas only a short distance away. This dry region is called a rain shadow. Some deserts and dry valleys exist partly because of this pattern. The effect can make two neighboring landscapes feel very different. One side forested and damp, the other open and dry. Rain shadows show how the shape of the land can guide the sky. A mountain range can divide moisture as quietly as it divides horizons. Monsoons are seasonal wind systems that can bring long periods of rain. During part of the year, land can warm faster than nearby ocean water. Warm air over the land rises, and moist air from the sea moves inward to replace it. As this moisture-rich air rises and cools, clouds build and heavy rains can develop. In another season, the pattern may weaken or reverse, bringing much drier weather. The word monsoon refers to this seasonal wind system, not simply to a single storm. Monsoon rains are important for farms, rivers, forests, and daily life in many regions. Their arrival can mark a major change in the year, when dry ground begins to receive water from a large, repeating movement of air. The rhythm belongs to both ocean and continent, repeating across the year. Inside thunderstorms, rain often forms in tall clouds built by rising warm air. On warm, humid days, air near the ground can become lighter than the air above it and begin to rise. As it climbs, it cools, and its water vapor condenses into cloud droplets. If the rising motion stays strong, the cloud can grow upward into a cumulonimbus cloud, a deep storm cloud with great vertical height. Inside it, droplets and ice particles move through powerful currents, growing until they are heavy enough to fall. The rain from such clouds can be sudden and intense because a large amount of water is being carried high and released quickly. A thunderstorm is a vertical engine, lifting moisture before letting it return in a concentrated shower. Its rain is shaped by height as much as by distance. Where different air masses meet, one can be lifted over the other and produce frontal rain. A warm air mass and a cold air mass do not mix instantly because they have different temperatures and densities. The warmer air is usually forced upward over the colder, heavier air. As the warm air rises, it cools, and its water vapor can condense into wide layers of cloud. This process may produce steady rain over a broad area, especially along warm fronts, where the lifting is gradual. Along cold fronts, the lift can be sharper and may bring heavier showers. Frontal rain is common in many middle latitude regions, where changing weather systems move across the land. It shows how rain can come from the meeting and layering of air. The boundary between air masses can become a long, quiet rainmaker. A large forest can return surprising amounts of water vapor to the air. Trees draw water from the soil through their roots, use it in their living tissues, and release some of it through tiny openings in their leaves. This release is called transpiration. Together with evaporation from wet surfaces and soil, it adds moisture to the lower atmosphere. In large forests, especially tropical forests, this recycled moisture can contribute to cloud formation and rainfall downwind. The forest is not just a place that receives rain. It can take part in the cycle, lifting water back toward the sky in invisible form. Each leaf becomes a small exchange point between ground and air, helping the landscape breathe moisture into the weather around it. A forest can be both a shelter from rain and a source of future rain. Once it reaches land, falling water helps shape rivers. Some rainfall sinks into the soil, while some flows over the surface as runoff. This moving water gathers into small channels, then streams, and then larger rivers. Along the way, it can carry grains of soil, sand, leaves, and minerals. Over long periods, repeated rainfall helps carve valleys, deepen stream beds, and move sediment toward lakes, wetlands, deltas, and seas. A single shower may seem brief, but many showers over many years can change the form of a landscape. Rivers are not separate from rain. They are one of rain's paths after it reaches the ground, guiding fallen water slowly back toward lower places. Every river carries a quiet memory of clouds in its slow-moving current. Over long spans of time, falling water can help weather stone and move minerals away. Pure water can affect rock, but rainwater often contains small amounts of dissolved carbon dioxide from the air, making it slightly acidic. This weak natural acidity can react with certain rocks, especially limestone, over long spans of time. The process can widen cracks, shape cliffs, and help form caves where water travels underground. Rain also enters tiny spaces in rock, where repeated wetting, drying, freezing, or thawing can loosen grains. These changes are usually slow enough to escape notice in a single lifetime, yet the effect is steady. Rain does not only wash the surface of the world, it can quietly take part in remaking stone itself. The softest weather can leave lasting marks on the hardest places. In cities, the path of a drop is often guided by rooftops, pavement, gutters, and drains. Natural soil can absorb some water, letting it sink downward and move slowly through the earth. Pavement, rooftops, and compacted ground do not absorb water in the same way, so rain often runs quickly into gutters, drains, and streets. This fast runoff can fill streams more suddenly than rain falling on fields or forests. Urban planners use drains, retention ponds, green roofs, rain gardens, and permeable surfaces to slow the water and give it places to go. In a city, rainfall becomes part of a design system as well as a natural one. Every curb, roof, and patch of soil helps decide whether rain lingers, sinks, or rushes away. The path of a drop may be shaped by stone, pipe, and pavement. When water reaches the ground, some of it can enter soil through a process called infiltration. Drops slip into tiny spaces between grains of sand, silt, clay, and organic matter. The speed of this movement depends on the soil's texture, structure, dryness, slope, and plant cover. Sandy soil often lets water pass quickly, while clay can hold water more tightly and slow its downward path. Roots, worm tunnels, and decaying leaves can create small channels that help water move below the surface. Gentle, steady rain often gives the ground more time to absorb moisture, while a sudden downpour may run away before much of it can sink in. Once inside the soil, the water becomes available to plants and soil organisms. It may remain near the surface for a while, or continue downward. Infiltration is one reason. A rainy day can support life long after the clouds have cleared. The water that disappears into the ground is not lost. It is quietly stored. Some of the water that sinks below the surface eventually helps refill groundwater. After water passes through soil, some of it keeps moving through layers of rock, gravel, or sand. These underground stores are called aquifers when they can hold and transmit useful amounts of water. The movement is usually slow, sometimes taking weeks, years, or far longer depending on the depth and the rock. Groundwater can later feed springs, wells, streams, and wetlands, even during dry weather. This means a rainfall may continue to matter long after it has stopped falling. The rain, seen at the surface, may become hidden water beneath fields, towns, forests, and hills. It travels through dark spaces where no sound of rain remains. In that quiet underground path, the sky becomes part of the Earth's reserve. In wetlands, rain is one source of steady or seasonal water. Marshes, swamps, bogs, and wet meadows often form where water gathers, moves slowly, or remains near the surface. Rain can help keep these places damp, especially when it joins water from streams, groundwater, or flooding rivers. Wetlands slow moving water and allow sediment to settle, which can make them important natural filters. They also provide habitat for plants, insects, amphibians, birds, and many small forms of life adapted to soaked ground. Some wetlands are wet all year, while others fill during rainy seasons and shrink during dry periods. Rain helps shape these changing patterns. A wetland can look still, but it is part of a careful water balance. Each rainfall may raise the surface slightly and refresh a hidden world. Before water touches the soil, leaves and branches may catch part of it. In forests, gardens, and grasslands, falling water often lands first on branches, bark, leaves, moss, or tall stems. This is called interception. Some of the water drips slowly to the ground, some runs down trunks and stems, and some evaporates back into the air without ever touching the soil. the shape of a plant, can change the way rain is delivered below. Broad leaves may gather drops and release them in heavier beads, while needles can hold fine droplets along their edges. This gentle sorting changes moisture patterns around roots and under canopies. Rainfall in a forest is therefore not just a direct fall from cloud to earth. It is softened, delayed, and redirected by living surfaces. The canopy becomes a quiet first landing place. On bare ground, individual drops can splash tiny particles of soil outward. Each falling drop carries a little energy, and when it hits exposed soil, it can splash tiny particles outward. This is called splash erosion. On a single rainy day, the movement may seem small, but repeated storms can loosen the surface and make it easier for water to carry soil away. Plant cover reduces this effect by catching drops before they strike with full force. Fallen leaves, grasses, moss, and roots all help protect the ground. Farmers and land managers often use cover crops, mulch, and careful planting to keep soil in place. Rain gives life to soil, but it can also disturb it when the surface is unprotected. The difference often depends on whether the ground is bare or gently covered. As drops form and fall, they can carry small dissolved substances from the air to the ground. As raindrops form and fall, they can absorb gases and collect tiny airborne particles. Some of these materials are natural, such as sea salt, dust, and traces of nutrients. Others may come from smoke, industry, vehicles, or fires. When the rain lands, it delivers these substances to leaves, soil, lakes, rooftops, and rivers. In small natural amounts, this can be part of the normal exchange between air and land. In polluted air, however, rain can carry materials that affect water and soil chemistry. A raindrop is therefore not perfectly pure when it reaches the earth. It has traveled through an atmosphere filled with invisible traces. Its clear appearance can hide a small record of the air it passed through. When certain pollutants enter the atmosphere, they can make rainfall more acidic than usual. The main sources are sulfur dioxide and nitrogen oxides, which can enter the air from burning fossil fuels and some natural processes. In the atmosphere, these gases can change into acids that mix with cloud droplets and falling rain. The rain still looks like ordinary water, but its chemistry can affect lakes, streams, forests, soils, and buildings over time. Limestone and marble are especially sensitive because acidic water can slowly dissolve their minerals. Acid rain became a major environmental concern in the 20th century because pollution could travel far from its source before falling. The subject shows that rainfall is connected to the condition of the air above it. What rises into the sky can return in a quieter form. A rainbow appears when sunlight is bent, reflected, and separated inside raindrops. A ray of sunlight entering a drop slows and bends because water and air carry light differently. Inside the drop, some of the light reflects from the back surface, then bends again as it leaves. Different colors bend by slightly different amounts, spreading the white sunlight into a band of colors. To see a rainbow, the sun is usually behind the observer, and raindrops are in the sky opposite the sun. Each person sees light from different drops at just the right angle, so a rainbow is partly a shared event and partly personal. The drops do not contain colored stripes of their own. They briefly arrange sunlight for the eye. Rain can therefore turn ordinary daylight into a visible lesson in light. During a shower, distant landscapes can appear softer because water changes the air between the viewer and the horizon. Falling drops scatter and block some light, especially when they are numerous, or when the rain is fine and steady. This can make hills, buildings, trees, and roads look pale or blurred. Heavy rain can reduce visibility so much that drivers and pilots must depend more carefully on instruments, lights, and distance. Mist, low cloud, and spray can add to the effect. The world itself has not changed shape, but the air has become filled with moving water. Rain places a thin, shifting curtain between the eye and faraway things. In a quiet shower, this can make a landscape feel gently layered. In a strong storm, the same process turns distance into a pale grey wall. In deserts, a brief shower can be rare and important. Many dry landscapes receive little rainfall over a year, and some places may wait a long time between showers. When rain does arrive, the ground may not absorb it quickly, especially if the surface is hard, crusted, or steep. Water can rush through dry channels called washes or wadis, sometimes appearing where no rain is falling directly overhead. Yet desert life is often prepared for these uncertain gifts. Seeds may wait in the soil until moisture arrives, and some plants grow, flower, and set new seeds quickly after rain. Animals may change their behavior when water collects in temporary pools. In a desert, rain is not just weather, it is a signal that awakens brief activity across a patient landscape. In tropical rainforests, heat, moisture, and living growth can help sustain frequent rainfall. Warm temperatures encourage evaporation from soil, rivers, and wet leaves, while trees release water vapor through transpiration. This moisture rises into the warm air, helping clouds form above or near the forest. In many tropical regions, rain can fall often because the air is warm, humid, and easily lifted. The forest canopy slows and divides the falling water, sending it down in drips, streams, and fine spray. Below, damp soil and shaded plants hold moisture after the shower passes. Rainforests are named for rain, but they are also active parts of the rainfall system. Their living surfaces keep water moving between earth and sky. The forest breathes moisture upward, and the sky returns it in falling drops. For agriculture, timing can matter as much as the total amount of rain. A field may need moisture when seeds germinate, when roots are expanding, or when crops are forming grain, fruit, or leaves. Rain that comes too early, too late, or all at once may be less useful than gentler rain at the right stage of growth. Too little water can stress plants, while too much can waterlog soil and reduce the air roots need. Farmers have long watched clouds, seasons, and soil moisture because rain is tied closely to harvests. Irrigation can help in some regions, but rainfall remains a central part of farming across much of the world. A shower over a field is more than a change in weather. It can become part of bread, rice, fruit, and daily meals. Falling drops can cool the air when some of their water evaporates. When some of the falling water changes from liquid into vapor, it uses heat from the surrounding air. This process is called evaporative cooling. In storms, cooled air can become denser and sink toward the ground, sometimes spreading outward as a gust of cooler wind before or during the rain. This is one reason the air may feel suddenly fresher when a shower begins on a warm day. The cooling effect depends on humidity, temperature, wind, and how much rain evaporates before reaching the surface. Rain is not only water falling downward, it also exchanges heat with the air around it. A warm afternoon can be gently changed by the hidden energy needed to turn liquid water back into vapor. Freezing rain forms when falling precipitation passes through layers of air with different temperatures. High in a cloud, water may begin as snow or ice. If it falls through a warm layer, it can melt into liquid rain. Below that warm layer, there may be a shallow layer of air below freezing near the ground. The drops do not have enough time to turn back into ice while falling, so they become supercooled liquid water. When they touch cold roads, branches, wires, or grass, they freeze into a clear coating of ice. Freezing rain is different from sleet, which usually refreezes into small ice pellets before reaching the surface. The difference depends on the depth and temperature of the air layers. A small change above the ground can decide what kind of precipitation arrives. Tiny living things can sometimes travel with falling water. Microbes, spores, pollen grains, and small fragments of organic material can be lifted into the air by wind, splashes, or rising currents. Some may become part of cloud droplets or fall back down with rain. Rain can also splash microbes from soil onto leaves, which is one reason plant diseases may spread more easily during wet weather. Not every droplet is biologically active, and most rain is simply water with traces of many materials. Still, rainfall can connect air, soil, plants, and surfaces in a moving exchange. The world above the ground is not empty between storms. It contains fine particles and living traces, some of which travel with water. Rain becomes one more path by which small life moves through the environment. Lakes are refilled, both by direct rainfall and by rivers and streams that feed them. A shower landing on a lake adds water at once, dimpling the surface with rings. More often, rain that falls across the surrounding watershed flows downhill through soil, ditches, wetlands, and channels before reaching the lake. The watershed is the land area that drains toward that body of water. When rain is steady, lake levels may rise gradually. During dry periods, evaporation and outflow may lower them again. This balance gives many lakes a seasonal rhythm. The surface may look still, but it is always connected to weather over a much larger area. A lake is not filled only by the rain that touches it. It also receives rain gathered quietly from the slopes and fields around it. After a heavy shower, rivers may change color and clarity. After a heavy shower, runoff may carry fine soil, clay, and organic matter from the land into streams. The water can turn brown, red, grey, or greenish depending on the minerals and particles in the watershed. In forested areas, dissolved plant material may give water a tea-colored tint. In mountain streams, glacial or rock flour can make water appear pale and milky. These changes are often temporary, settling as flow slows or particles are carried downstream. Clear water is not always healthier than colored water because natural rivers vary widely. Rain simply reveals what the water is moving through and carrying with it. A river after rain can become a visible mixture of landscape, soil, leaves, and stone, all traveling together. A dormant seed may begin to wake when enough water reaches it. Many plants produce seeds able to survive dry or cold periods until conditions improve. Moisture softens seed coats, activates enzymes, and allows the first root to emerge. In some environments, rain is one of the clearest signals that the season is safe enough for growth. This is especially important in dry grasslands, deserts, and places with strong wet and dry seasons. Not all seeds respond to the first shower. Some need repeated moisture, certain temperatures, or other cues. This helps prevent them from sprouting during a brief wet spell that will not last. Rain is part of the message, but not always the whole message. When the conditions are right, a quiet fall of water can begin the first movement of a new plant. For thousands of years, human shelter has been shaped by falling water. Roofs, walls, gutters, drains, and raised floors are all responses to falling water. In wet climates, steep roofs can shed rain quickly, while wide eaves help keep walls and doorways drier. In drier regions, flat roofs may be more practical, where heavy rainfall is less common. Traditional buildings often reflect local weather patterns, using materials and shapes suited to the rain they receive. Modern architecture continues this quiet conversation, with water through waterproof layers, sealed windows, storm drains, and careful grading around foundations. A house is not only a place built against cold or heat, it is also built with rain in mind. Every roofline shows a simple understanding: water must be guided, slowed, collected, or led safely away. Weather radar can reveal rain before it reaches an observer on the ground. Radar works by sending out pulses of radio energy and listening for the signals that bounce back from raindrops, snowflakes, or hailstones. Larger and more numerous particles usually return stronger signals, helping meteorologists estimate where precipitation is falling and how intense it may be. Modern radar can also detect motion toward or away from the radar, which helps show wind patterns inside storms. On a weather map, the moving patches of color are a simplified view of countless drops suspended and falling through the air. Radar does not catch every detail perfectly, especially far from the instrument or in complex terrain. But it gives a wide view that human eyes cannot. It turns hidden rain inside clouds into a visible pattern across the landscape. Satellites help track rain over oceans and remote regions where ground instruments are sparse. From high above Earth, satellites observe cloud shapes, temperatures, moisture, and sometimes the signals related to falling precipitation. This is especially useful over wide seas, deserts, mountains, and forests where rain gauges may be few. Some satellites carry sensors that can estimate rainfall by looking at microwave energy, which can pass through clouds better than ordinary visible light. The measurements are not as simple as catching water in a gauge, but they help build a larger picture of global rainfall. With satellites, scientists can follow storm systems across oceans and watch seasonal rain belts shift through the year. A single shower may be local, but from space, rain becomes part of a planet-wide pattern, moving in bright clouded bands around the Earth. Forecasting rain requires both observation and mathematical models of the atmosphere. Meteorologists begin with measurements of temperature, pressure, humidity, wind, and cloud conditions from many places. Computers then use physical equations to estimate how the atmosphere may change. Because air is always moving and interacting, small differences in starting conditions can affect the forecast, especially several days ahead. This is one reason rain predictions often include probabilities. A forecast chance of rain usually means the probability that measurable precipitation will fall at a given location during a specified time period. Short-term forecasts may use radar to follow showers already forming, while longer forecasts depend more heavily on models. Predicting rain means reading an atmosphere that is never still. The forecast is a careful estimate of where moisture, lift, and cooling may meet. A sun shower occurs when rain falls while the sun is still shining nearby. This can occur when a small shower cloud passes through a bright area of sky, or when wind carries raindrops away from a cloud into sunlight. From the ground, the combination may feel unusual because sunshine and rain are often imagined as opposites. In reality, the sky can hold both at once, especially when showers are scattered and broken. Sun showers are also good conditions for seeing rainbows because sunlight may enter falling drops, while the darker rain cloud remains ahead of the observer. The rain itself is not different from ordinary rain. What changes is the arrangement of cloud, sun, wind, and viewpoint. A sun shower is a small reminder that weather rarely fills the sky evenly. It often arrives in overlapping layers. Along coasts, sea breezes can help shape afternoon rainfall. During the day, land often warms faster than nearby ocean water. Warm air over the land rises, and cooler, moist air from the sea moves inland to replace it. Where this sea breeze meets warmer air over land, the air can be lifted, helping clouds grow. In humid regions, this lifting can produce afternoon showers or thunderstorms, sometimes in narrow zones just inland from the coast. The exact pattern depends on coastline shape, wind direction, temperature, and available moisture. Sea breeze rain is one way the border between land and ocean influences local weather. A beach may feel clear in the morning, while clouds gather farther inland later in the day. Rain can begin where two slow-moving breaths of air meet. Atmospheric rivers are long, narrow corridors of moist air that can carry large amounts of water vapor. They usually form over oceans and move with weather systems, transporting moisture toward land. When this moist air is lifted by mountains or frontal boundaries, it can produce widespread rain or snow. The name may sound dramatic, but it describes an invisible flow in the atmosphere rather than a river with banks. Some atmospheric rivers bring helpful water to regions that depend on winter storms, while especially strong ones can bring too much rain at once. Their importance comes from scale. A moving band of vapor can connect distant ocean moisture with mountains, valleys, and reservoirs. Rain from an atmospheric river is the surface expression of a hidden stream overhead, traveling through the air before touching the ground. A city can sometimes shift rainfall differently on its upwind and downwind sides. Urban areas often hold heat because buildings, roads, and dark surfaces absorb and release warmth. This is called the urban heat island effect. Warmer air over a city may rise more easily, and rough building surfaces can disturb the wind. In some cases, these changes can help clouds grow or slightly shift where showers form or intensify downwind. Pollution particles may also affect cloud droplets, though the results can be complex and vary from place to place. Cities do not simply sit beneath weather. They can sometimes influence the lower atmosphere around them. The effect is usually subtle compared with large weather systems, but it shows how human-built surfaces take part in the path of rain. Even rainfall can carry traces of urban shape and warmth. Fresh rainfall is naturally soft because it begins with little dissolved mineral matter. As water evaporates from oceans, lakes, and soil, most salts and minerals are left behind. The vapor rises, condenses into cloud droplets, and later falls as rain, with relatively low mineral content. Once the water lands, it may collect minerals from soil, pipes, rocks, or containers. This is why groundwater and river water often taste and behave differently from fresh rainwater. Soft water can lather more easily with soap because it has fewer calcium and magnesium ions than hard water. Rain is not perfectly pure, since it can pick up gases and particles from the air. But compared with the many natural waters on land, it usually carries fewer dissolved minerals at the moment it falls. Its softness reflects the separating power of evaporation. Collecting rainfall for later use is an old and practical human habit. People have done this for thousands of years in dry lands, farms, towns, and island communities where fresh water can be limited. A simple system may guide roof runoff into a barrel or tank. Larger systems may include filters, covered cisterns, channels, and storage ponds. The collected water can be used for gardens, livestock, cleaning, or, when properly treated, drinking. Its use must match local rules and water quality needs, because roof materials, dust, animals, and containers can affect safety. Harvesting does not create new water, but it slows the journey of water that might otherwise run quickly away. A roof becomes more than shelter in such a system. It becomes a quiet collecting surface, turning passing showers into a stored reserve for drier days. In limestone caves, falling water can eventually help build stalactites and stalagmites. When rainwater passes through soil, it often absorbs carbon dioxide, becoming weakly acidic. This water can dissolve small amounts of limestone as it seeps downward through cracks. When it reaches the open air inside a cave, some carbon dioxide escapes, and the dissolved minerals can be left behind as calcite. Over long periods, deposits hanging from the ceiling become stalactites, while those rising from the floor become stalagmites. Growth is usually very slow, often measured over many years or centuries. A cave formation may therefore be a record of countless small seepages from rain above. The water that once fell on grass, trees, or bare rock continues its work underground. In the stillness of a cave, rain becomes stone by adding one thin layer at a time. On the ocean, a shower can briefly change the surface itself. When drops strike seawater, they create tiny rings, splashes, and bubbles. Heavy rain can roughen the surface in some ways, while also smoothing very small wind-made ripples in others. Fresh rainwater is less salty than seawater, so a strong shower can create a thin, fresher layer near the surface, before waves and currents mix it downward. Rain also transfers a little momentum and energy into the upper ocean. Over a wide stormy area, these small impacts can add up, especially when combined with wind. From a ship or shoreline, rain on the sea can look like a textured veil moving across the water. The ocean is vast, but its surface still responds to each falling drop. Even open water receives rain as touch. The upper layers of lakes and ponds can also respond to a shower. Falling drops add water, disturb the surface, and can bring cooler temperatures into the shallow top layer. During warm seasons, many lakes develop layers, with warmer water above and cooler water below. A heavy or cool rain may help mix some of the surface water, especially when wind is present. It can also wash leaves, soil, and nutrients from the surrounding land into the water. These changes affect light, clarity, oxygen, and the small organisms that live near the surface. A gentle rain may leave only rings and soft sounds, while a stronger rain becomes part of the lake's chemistry and movement. The surface of a lake is not merely a boundary. It is a meeting place where air, land, and falling water exchange their effects. For mushrooms, wet weather often provides the moisture that makes hidden fungal life visible. The main body of a fungus is usually hidden as a network of fine threads called mycelium, growing through soil, wood, or leaf litter. When conditions become damp enough, some fungi produce mushrooms, which are their visible fruiting bodies. Rain softens the environment, supports the movement of nutrients, and helps keep the mushroom from drying out as it releases spores. This is why mushrooms often appear after wet weather, especially in shaded forests, lawns, and fallen wood. Not every mushroom comes from a single shower, because temperature, season, and species also matter. Still, Rainfall is often the signal that makes hidden fungal life briefly visible. After rain, the forest floor can reveal forms that were already growing quietly beneath leaves and bark. Mosses often revive quickly after a shower because many of them tolerate drying out. Unlike flowering plants, mosses do not have deep roots that draw water from the soil. They absorb much of their moisture directly through their surfaces. During dry periods, some mosses curl, darken, or become brittle-looking, slowing their activity until water returns. When rain falls, their tiny leaves can swell and unfold, often becoming brighter and softer within a short time. This ability allows mosses to live on rocks, tree trunks, walls, and thin soils where water may not remain long. Rain does not merely water moss from below. It touches the plant directly, restoring its living surface. A patch that seemed almost asleep can become vivid again after a shower. Moss shows how small plants can be tuned closely to passing moisture. Lichens often become more active when rain wets their surface. A lichen is a partnership, usually between a fungus and a photosynthetic partner, such as an alga or cyanobacterium. Many lichens can survive long dry periods by slowing their metabolism. When rain or mist returns, they absorb water and begin photosynthesis again if light is available. This makes them well suited to rocks, bark, roofs, and exposed ground where moisture comes and goes. Some lichens change color noticeably when wet, appearing greener, brighter, or more flexible than when dry. They do not need soil in the ordinary sense, but they do need moments of moisture. Rain gives these quiet partnerships time to function. A stone wall after a shower may hold many small living patches, each briefly awakened by water from the sky. During or after wet weather, earthworms often appear at the surface. One reason is that moist conditions make it easier for them to move across the ground without drying out. The surface becomes safer for travel than it would be on a hot, dry day. In some cases, soaked soil may also change the air spaces underground, encouraging worms to move upward or sideways. Contrary to a common belief, many earthworms do not immediately drown in wet soil. They can survive for a time if enough oxygen is present. Rain simply changes the conditions around them. It softens the soil, reduces drying risk, and opens temporary roots across lawns, paths, and forest floors. A rainy morning can reveal animals that normally remain hidden below our feet. Their brief appearance is part of the soil's quiet life. When wet conditions return, frogs and toads often become more active. Their skin must stay moist, and many species use wet conditions for movement, feeding, and breeding. Rain can fill temporary pools, soften the ground, and raise humidity, making it easier for amphibians to travel between hiding places and water. In many regions, the sounds of calling frogs are strongly tied to rainy seasons or warm, wet nights. These calls help individuals find mates near ponds, ditches, marshes, or small pools that may not last all year. Rain therefore creates both a pathway and a meeting place. It changes a dry landscape into one with temporary water and safer air for delicate skin. The arrival of rain may seem like a simple weather change to people, but for amphibians, it can open a whole season of movement. Birds respond to rain in many practical ways. Light rain may not stop them from feeding, especially if food is plentiful and winds are gentle. In heavier rain, many birds shelter in trees, shrubs, reeds, cliffs, or building edges, turning their bodies to reduce heat loss and keep feathers from becoming too wet. Feathers are not just decoration. They help insulate the body and shed water when properly preened. Some birds bathe in rain, spreading their wings or fluffing their feathers to let water reach the surface. Rain can also change food availability, bringing insects out or making worms easier to find. For birds, rain is neither simply good nor bad. Its effect depends on temperature, wind, intensity, and need. A shower becomes part of the daily calculation of warmth, safety, and food. After dry weather, a shower can wash particles from leaves and air. Dust, pollen, soot, salt, and fine soil can settle on leaves, windows, roofs, and cars during dry weather. When rain arrives, some of these particles dissolve, loosen, or flow away with runoff. This is why plants may look brighter after a shower, especially where dust has muted their color. Rain can also remove some airborne particles, making the air feel clearer once a storm has passed. The effect is temporary because new particles continue to arrive from wind, traffic, soil, plants, and sea spray. Still, a fresh rainfall can reset the surface of a place. It traces the shapes of leaves, cleans ledges, darkens tree bark, and gathers fine dust into small flowing lines. Water makes the hidden layer of dryness visible as it moves away. Wet surfaces often look darker and richer because they reflect light differently from dry ones. When water fills tiny, rough spaces in stone, saw, soil, bark, cloth, or pavement, less light is scattered back in a pale, diffuse way. More light enters the surface and is absorbed, so the material may look darker and richer. This is why a road turns dark grey after a shower, and why tree trunks can appear more deeply brown or black. Leaves may shine because water forms smooth films and droplets that reflect bright highlights. The color change is not a new pigment, but a change in the way light meets water and surface texture. Rain temporarily alters the appearance of the world without repainting it. After the surface dries, the colors often return to their lighter state, as if the brightness has slowly lifted. Wind can tilt falling rain before it reaches the ground. Raindrops fall under gravity, but they are also carried sideways by moving air. In a light breeze, this may create a gentle slant, making rain touch one side of a window, tree trunk, or wall more than the other. In stronger winds, drops can travel at a sharper angle and strike vertical surfaces that would stay drier in calm weather. This is called wind-driven rain, and it matters for buildings, forests, and exposed cliffs. Roof overhangs, shutters, sealed joints, and drainage details often exist, partly because rain does not always fall straight down. The path of a drop is shaped by both its weight and the air around it. A storm can therefore right its direction across the landscape, leaving one side wet and the other partly sheltered. Beneath a cloud, grey rain streaks can reveal the motion of air. From a distance, a shower often looks like a grey curtain, but its edges may lean, bend, or fray. These shapes reveal falling water being pushed by wind as it descends. Sometimes the top of a rain shaft remains close to the cloud, while the lower part drifts away, showing that winds differ at different heights. Stronger downdrafts can make rain look heavier near the center of a shower, while drier air can thin the edges through evaporation. The scene may last only a few minutes before the cloud moves on or changes shape. A rain shaft is not just water falling from above. It is a visible trace of invisible air currents, drawn softly in grey against the sky. In soft dust or dry soil, individual drops can leave small craters. When a drop hits a loose surface, it pushes grains outward and may leave a tiny round mark with a raised rim. These marks are usually fragile and can vanish with the next drops, a gust of wind, or a passing footstep. In some places, ancient raindrop impressions have been preserved in sedimentary rock, showing that rain fell on soft surfaces long before humans existed. Such marks are simple, but they can carry a clear message from the past. The surface was exposed to air, soft enough to receive drops, and then covered before the impressions disappeared. Rain normally seems too gentle to leave a fossil trace, yet under the right conditions, its smallest impacts can be recorded. A brief shower can become part of stone memory. On bare or fragile slopes, flowing water can form rills and gullies. At first, runoff may move as a thin sheet across the surface. If the flow gathers into small paths, it can begin cutting narrow channels called rills. With repeated storms and enough loose material, some channels deepen and widen into gullies. This process is influenced by slope, soil type, vegetation, rainfall intensity, and how land is used. Plant roots and surface cover can slow the water and hold soil together, while exposed ground is more easily carved. Rills and gullies are not made by one drop, but by many drops becoming moving water. They show how rainfall can shift from a soft fall into a shaping force. On a hillside, the path of runoff can become a line written slowly into the land. In places that are dry most of the year, enough water can briefly fill temporary streams. These channels may look empty for weeks or months, holding only stones, sand, or cracked mud. When enough rain falls in the surrounding area, water begins to gather and move through them, sometimes quickly. Such temporary streams are common in drylands, seasonal climates, and rocky landscapes where runoff flows faster than it can soak in. Though brief, these flows can move sediment, refill pools, spread seeds, and provide water for animals. They also help shape the channel for the next rainy event. A dry stream bed is not always abandoned. It may be waiting for the right storm over the right part of its watershed. Rain gives it motion for a while, turning a quiet line in the land into moving water. At the base of slopes, repeated runoff can help build alluvial fans. When water rushes down a steep valley or canyon, it can carry gravel, sand, and finer sediment. As the flow reaches flatter ground, it slows and spreads outward. With less energy, the water drops much of its load, building a fan-shaped deposit over time. Many alluvial fans are found near mountains in dry or semi-dry regions, where sudden rains can move sediment in short, powerful bursts. The fan does not form all at once. It grows through repeated flows, each adding material in slightly different paths. From above, the shape can look like a pale hand opening from the mouth of a valley. Rainfall, slope, and sediment work together to create this quiet pattern, where moving water gradually lays the mountain down. Compacted ground may soften when wet, but it does not always absorb water easily. When soil has been pressed by feet, wheels, animals, or heavy machinery, the spaces between its particles become smaller. Water then has fewer paths downward, so rain may collect on the surface or run away rather than sinking in. In gardens, farms, parks, and footpaths, compacted soil can make puddles more likely and roots less comfortable. Over time, plant roots, worms, careful digging, added organic matter, and reduced pressure can help restore some of the soil's openings. Rain reveals the condition of the ground it falls on. If water disappears gently, the soil has room to receive it. If it lingers or runs, the surface may be sealed or crowded. The behavior of rain becomes a simple test of hidden structure. After a fire, loose ash can turn into moving mud and sediment when storms arrive. When vegetation has burned, the ground may have less cover to slow falling drops and less root strength to hold soil in place. Some burned soils can also become water repellent for a time, causing rain to run off quickly instead of soaking in. On steep slopes, this runoff can carry ash, soil, stones, and burned plant material downhill. The result may be muddy flows or heavy sediment in streams after storms. The process is not caused by rain alone, but by rain meeting a landscape whose surface has changed. In time, plants may return and soil structure may improve. Rain then becomes part of recovery as well as disturbance. It can move the remains of fire downward while also helping new growth begin. Decomposition often speeds up when dead leaves, wood, and soil organisms stay moist. In a dry place, fallen plant material may remain crisp and slow to break down. When rain wets the surface, fungi, bacteria, insects, worms, and other small organisms can become more active. They gradually turn leaves, stems, and wood into simpler materials that enrich the soil. This process releases nutrients that plants can use again, linking rainfall to the quiet recycling of forests, gardens, and fields. Too much water can slow some decomposition if oxygen becomes scarce, but moderate moisture often helps the work proceed. A wet layer of leaf litter may look still, yet it is filled with slow change. Rain does not only help plants grow upward, it also helps old plant material return to the earth below. As water passes through a canopy, it can carry nutrients from leaves and branches to the soil. As water moves across plant surfaces, it may wash off dust, pollen, tiny fragments, and dissolved substances from the leaves themselves. This water, called throughfall, when it passes through a canopy, can be slightly different in chemistry from rain that falls in open air. Some water also runs down trunks and stems, concentrating moisture near the base of plants. In forests, these pathways help move small amounts of nutrients into the root zone. The amounts vary with species, season, pollution, and the condition of the canopy. Rainfall in a woodland is therefore changed by the living roof it passes through. By the time it reaches the ground, it has touched bark, leaves, lichens, and mosses. It carries a faint signature of the canopy above. Many rainforest leaves have pointed tips that help shed rain. These tips are often called drip tips, and they allow water to run off the leaf more easily. In very wet environments, lingering water can block light, add weight, and encourage the growth of fungi or algae on leaf surfaces. A smooth leaf with a narrow point can guide drops away, keeping the surface clearer for photosynthesis. Not every rainforest plant has this feature, and leaf shape is influenced by many needs at once, including light, heat, insects, and growth form. Still, drip tips are a common and easy to see adaptation in many wet, tropical forests. They show how frequent rain can influence even the outline of a leaf. A small point at the end of a green blade may be part of a quiet design for living under heavy showers. Some plants collect rainwater in their leaves and hold small pools above the ground. Bromeliads are a well-known example, especially in tropical forests, where their leaves can form a cup or tank. These little reservoirs catch rain, fallen bits of leaves, and tiny particles. Insects, frogs, microbes, and other small organisms may use the water, creating a miniature habitat high in the branches or close to the forest floor. The plant can absorb some nutrients from material that gathers there, although different species use the pool in different ways. Rain turns the plant's shape into a container. Instead of letting every drop run straight to the soil, the leaves pause part of the rainfall in a living bowl. A single shower can fill many small green basins that would be almost invisible from below. Pollination can pause or change when wet weather affects pollen and insect movement. Many flowers rely on dry, powdery pollen that can be carried by bees, butterflies, flies, wind, or other agents. Heavy rain may wash pollen away, make it clump, or keep pollinating insects under shelter until the weather improves. Some flowers close during wet conditions, helping protect their reproductive parts. Others hang downward or have shapes that shield pollen from direct rainfall. Rain is not always a problem, because it also supports the plants that produce flowers and the habitats where pollinators live. Its effect depends on timing, intensity, and the species involved. A shower during full bloom can briefly pause the traffic of insects and pollen. When the air clears, the work may resume, with petals drying and visitors returning to the flowers. Some plant diseases spread more easily when splashing drops move spores or bacteria. When drops strike an infected surface, tiny droplets can leap outward and carry microscopic material to nearby plants. Wet leaves may also stay damp long enough for certain fungi to grow or enter plant tissues. Gardeners and farmers often notice that some diseases become more common during warm, rainy periods, especially when plants are crowded and air moves poorly between them. This does not make rain harmful by itself. Plants need water, and many thrive with regular showers. The issue is the combination of moisture-susceptible plants and disease organisms. Rain creates the wet surface and movement that some microbes use. In the quiet space between leaves, a shower can connect one plant to another through splashes too small to see. Soft mud after a shower can preserve clear tracks of animal movement. Soft, wet ground records footprints better than dry soil, especially near ponds, paths, riverbanks, and forest edges. Deer, foxes, birds, dogs, insects, and many other animals can briefly mark the surface as they pass. The shape, spacing, and depth of the tracks may suggest the animal's size, direction, and pace. These signs are temporary. More rain can blur them, sunlight can harden them, and wind or footsteps can erase them. For naturalists, fresh rain can make a landscape easier to read because it smooths older marks and prepares a new surface. After a shower, the ground becomes like a soft page. Animals write on it without intending to, leaving quiet evidence of lives that often remain out of sight. For insects, wet weather can change shelter, flight, breeding places, and daily activity. Some insects shelter under leaves, bark, stones, or soil when heavy drops would make flight difficult. Small flying insects are especially affected because raindrops can be large compared with their bodies. Others become more active after rain. When humidity rises, plants are fresh, and puddles or damp soil create new opportunities. Mosquitoes, for example, often depend on standing water for their early life stages, though different species use different kinds of water. Ants may adjust nest openings or move brood if flooding threatens. Rain is therefore a physical event for insects as much as a source of moisture. It changes air, ground, shelter, and breeding places all at once. To a small creature, a shower can be a major change in the shape of the day. Temporary pools can freshen after rainfall and support short-lived aquatic life. After enough rainfall, hollows in rock, soil, tree bases, fields, or roadside ditches may fill with water. These pools may last only days or weeks, but they can support algae, insect larvae, tiny crustaceans, amphibian eggs, and microbes adapted to brief wet periods. Some organisms survive the dry interval as eggs, cysts, spores, or resting stages, waiting until water returns. Because fish are often absent from temporary pools, certain small animals can develop there with fewer predators. The pool is simple in appearance, but it may hold a quick, active world. Rain gives such habitats their beginning, and evaporation slowly brings them toward an end. Between those moments, a shallow patch of water can become a small seasonal home. In estuaries, extra fresh water can shift the balance between river water and seawater. An estuary is a place where river water mixes with seawater, often near a coast. After heavy rain upstream, more fresh water may flow into the estuary, lowering salinity near the surface or pushing saltier water farther seaward. During dry periods, ocean water may reach farther inland. Plants, fish, shellfish, and plankton in estuaries are adapted to changing conditions. But the timing and size of freshwater pulses still matter. Rain can also carry sediment and nutrients from the watershed into the mixing zone. An estuary is never simply river or sea. It is a shifting meeting place, and rainfall helps set the rhythm of that meeting. A storm far inland can quietly change the water, where tides move among reeds and channels. Along coasts, runoff can carry material from land into the sea. Water running through streets, fields, forests, and rivers may pick up soil, leaves, nutrients, oils, plastics, or other traces of human and natural activity. When this runoff reaches the coast, it can change water clarity and chemistry, especially near river mouths and storm drains. In natural amounts, sediment and nutrients help build deltas, feed wetlands, and support food webs. In excess, they may create problems for water quality. The effect depends on land use, rainfall intensity, tides, currents, and the shape of the coastline. Rainfall therefore links inland surfaces with marine environments. A drop that lands on a hill or sidewalk may eventually become part of a coastal plume, carrying a small piece of the land outward into the sea. Deltas grow partly because rivers carry sediment toward their mouths. As a river approaches a lake or sea, its flow often slows, and the sand, silt, and clay it carries can settle out. Over long periods, this builds low, flat land cut by many channels. Rain contributes by feeding the river system and helping erode and transport sediment from the watershed. Deltas are shaped by a balance between river deposits, waves, tides, storms, and sinking ground. They can be fertile and rich in wetlands, but they are also changeable places because water is always rearranging them. A delta is not built by rain alone, but rain is part of the supply line. Far upstream showers may help move tiny grains that one day settle near the coast. In this way, rainfall can help rivers make land. Across the planet, rainfall helps shape climate zones. Places near the equator often receive frequent rain because warm air rises easily, cools, and forms deep clouds. In many subtropical regions, sinking dry air makes rain less common, helping create broad desert belts. Farther toward the poles, storm tracks and ocean currents influence where rain and snow are most likely to fall. Mountains, coastlines, forests, and prevailing winds add smaller patterns inside these larger zones. Climate is not just the average temperature of a place. It is also the expected rhythm of water from the sky. A forest, grassland, desert, or tundra reflects, in part, how much rain arrives and when it comes. Over long spans of time, rainfall helps decide which plants can live, which soils form, and how water moves through the landscape. The intertropical convergence zone is a shifting belt where rising air often brings heavy rain. Near the equator, trade winds from the northern and southern hemispheres meet and push warm, moist air upward. As the air rises, it cools and forms towering clouds, showers, and thunderstorms. This zone does not stay fixed in one place. It moves north and south through the year as the strongest heating follows the seasons. In many tropical regions, its movement helps create wet and dry seasons. From space, it can appear as a band of clouds circling much of the globe. On the ground, its passage may be felt as weeks of more frequent rain. The pattern is large, but its effect is local. A village, forest, or field may receive its rainy season because this broad atmospheric meeting line has drifted overhead. Tree rings can preserve traces of wetter and drier years. In many regions, trees grow wider rings during favorable years and narrower rings during stressful years, where moisture is the main limit on growth. Ring patterns can reveal years of wetter or drier conditions. Scientists compare living trees with older wood from buildings, fallen logs, or preserved trunks to extend these records back in time. The rings do not measure rainfall directly, because temperature, sunlight, soil, disease, and age also influence growth. Still, when carefully studied, they can help reconstruct long patterns of drought and rain before modern instruments existed. A tree's trunk is therefore more than wood. It can be a quiet archive of seasons. Each ring carries a small trace of the weather that helped or hindered growth during one year. Cave formations can also hold chemical clues about past rainfall. As rainwater seeps through soil and rock, it carries dissolved minerals into caves, where stalagmites and stalactites may grow layer by layer. The chemistry of these layers can reflect changes in rainfall, vegetation, temperature, and the path water took underground. Scientists study features such as oxygen isotopes, which are forms of oxygen that vary slightly in mass and can reveal clues about past water. The evidence is complex and must be interpreted carefully, but it can reach far beyond written weather records. A polished slice of cave calcite may hold alternating bands formed by water that once fell as rain above. In the darkness of a cave, the outside climate can leave a slow mineral diary. Drop by drop, rainfall becomes a record that can last for thousands of years. Fresh water from the sky helps maintain the ocean salinity balance. The sea is salty because dissolved minerals are delivered by rivers, seafloor processes, and other long-term sources, while evaporation removes water, but leaves most salts behind. Rain returns fresh water directly to the ocean surface and indirectly through rivers. In rainy regions, the surface ocean can become slightly less salty, especially when large storms or river outflows add a great deal of fresh water. In dry, hot regions with strong evaporation, surface waters can become saltier. These differences in salinity help influence ocean density, mixing, and circulation. A raindrop is tiny compared with the sea, but rain is part of the ocean's water balance. Over wide areas and long times, falling fresh water helps shape the character of the upper ocean. The movement of water through the atmosphere also affects how heat travels around Earth. Water evaporates from warm surfaces, carrying energy as hidden heat in water vapor. When that vapor condenses into cloud droplets, much of the stored energy is released into the atmosphere. This release helps power storms and influences wind patterns. Tropical rain systems are especially important because they move heat upward from warm oceans and land surfaces. The rain seen at the ground is only one part of a larger energy exchange. Before a drop falls, water has already absorbed heat, traveled as vapor, and helped build clouds. Rain is therefore connected not only to moisture, but also to the planet's flow of warmth. A shower may feel cool on the skin, yet it belongs to a process that moves heat through the sky. From year to year, rainfall patterns can shift as oceans and the atmosphere interact. One important example is El Niño and La Niña, a natural cycle involving sea surface temperatures and winds in the tropical Pacific. During El Niño, warmer waters in parts of the central and eastern Pacific can shift where clouds and rain form. During La Niña, cooler waters and different wind patterns can shift rainfall in other ways. The effects are not identical everywhere, and local weather still depends on many factors. Some regions may become wetter than usual, while others become drier. These changes show that rain in one place can be linked to conditions far away over the ocean. The sky above a field or city may carry the influence of distant waters. Rainfall is local in arrival, but often global in cause. A cloudburst occurs when a large amount of water falls in a short time. The word is often used for sudden, intense rainfall from a strong shower or thunderstorm. In such events, the ground may not absorb water fast enough, so runoff forms quickly on streets, hillsides, or dry streambeds. Cloudbursts are most likely when moist air rises strongly and a storm releases water over a limited area. The exact amount needed to define a cloudburst varies by region and usage, so it is better understood as a description of intensity rather than a single universal measurement. Though brief, this kind of rain can reshape small channels, fill low places, and reveal every slope in the land. It shows how rainfall is not only measured by totals over a day, but also by how quickly the water arrives. Flooding can begin when more water arrives than the land and rivers can hold. Flooding may follow long, steady rain that slowly fills a watershed, or intense rain that sends water rushing over the surface. The result depends on soil moisture, slope, vegetation, river shape, drainage systems, and how much space water has to spread. Floodplains are natural low areas beside rivers where water can expand during high flow. When people build on them, the same natural spreading can become a serious problem. Rain is not the only cause of floods, but it is one of the most common starting points. The process is a matter of balance. A landscape can receive and store some water, but when that capacity is exceeded, rain becomes moving water seeking the lowest paths available. Across cultures, rainfall has influenced language, calendars, and daily routines. In regions with strong wet and dry seasons, the first rains may mark a practical turning point for planting, travel, herding, or gathering. Words for different kinds of rain often become rich and specific, because people notice whether rain is gentle, slanting, cold, warm, brief, steady, or delayed. Songs, proverbs, stories, and festivals can reflect the hope, patience, and observation tied to rainfall. These cultural meanings vary widely and should not be reduced to one simple idea. What they share is attention. Rain is not only a physical event measured by gauges. It is also part of how communities read time, work with land, and remember seasons. A clouded sky can carry meanings shaped by generations of watching water return. Around a shower, the air often feels different because humidity changes. Humidity is the amount of water vapor in the air, and it affects how easily water evaporates from skin, soil, leaves, and wet surfaces. When air is humid, evaporation slows, and warmth may feel heavier. When rain falls through dry air, some drops evaporate, cooling the air and raising humidity below the cloud. After rain, the ground, plants, and pavement may continue releasing moisture back into the air. This is why a place can feel fresh, damp, cool, or close, depending on temperature and wind. Rain is liquid when it reaches the ground, but it is surrounded by invisible vapor. The atmosphere around a shower is a mixture of falling water, evaporating water, and air adjusting to both. Wildfire risk can rise or fall as wet and dry periods change moisture in plants and soil. After enough rainfall, grasses, leaves, branches, and the upper soil can hold more water, making them less likely to burn easily. During long dry periods, that moisture declines, and dead plant material can become more flammable. The relationship is not always simple. Rainy seasons may encourage plant growth, and if that growth later dries, it can add fuel. The timing, amount, and follow-up weather all matter. Fire weather specialists pay attention not only to recent rain, but also to temperature, wind, humidity, and the condition of vegetation. Rain is one of the quiet controls in this larger pattern. It can cool and moisten a landscape for a time, shaping how ready the living and dead vegetation is to burn. In grasslands, the amount and timing of rainfall help decide which plants can survive. Too little rain may favor sparse desert shrubs or hardy dryland plants. More regular rainfall can support grasses, wildflowers, and deep-rooted perennials. In many grasslands, rain arrives seasonally, and plants respond with bursts of growth when moisture is available. Their roots often extend deeply or spread widely, helping them capture water during favorable periods and survive dry intervals. Grazing animals, fire, soil type, and human land use also shape grasslands, but rainfall sets one of the basic limits. A grassland may look open and simple, yet its life is tuned to a careful water rhythm. The height, density, and greenness of the plants often reflect recent showers and longer climate patterns. Rain helps decide whether the land carries a thin cover or a waving field of stems. Seasonal rainfall can influence animal migration and breeding. In some regions, new plant growth after rains provides food for grazing animals, insects, and the predators that follow them. Temporary pools may support amphibian breeding, while wet season blooms can attract birds or pollinators. Animals do not respond to rain alone. Day length, temperature, food, inherited behavior, and landscape memory also matter. Still, rainfall can be a powerful signal where dry months are followed by a wet season. It changes the availability of water, shelter, and food across large areas. A herd moving toward greener ground, a frog calling from a new pool, or insects emerging after a storm may all be part of this response. Rain can turn a quiet season into a time of movement. Even within the same storm, the amount of water reaching the ground can vary from place to place. Inside a cloud, some areas have stronger rising air, larger droplets, or more ice particles than others. Winds can push the falling rain sideways, while evaporation can reduce drops in drier air below. As the cloud moves, One part of a town may receive a heavy shower, while another receives only a trace. This unevenness is why rain gauges only a short distance apart can record different amounts. Weather radar helps show the pattern, but a single gauge still tells the story of one point on the ground. Rainfall is often a patchwork rather than a smooth blanket. Each measured amount is true for its place, while the wider storm remains full of small variations. Careful measurement of rainfall covers only a short part of human history. Simple gauges are old, and some societies kept rainfall records many centuries ago, but widespread standardized measurement developed much later. Today, rain gauges, radar, satellites, and computer systems create detailed records across many regions. These records help farmers, engineers, climate scientists, water managers, and weather forecasters understand patterns and risks. Yet even modern measurements have gaps, especially over oceans, mountains, forests, and remote areas. This means rainfall knowledge is both precise and incomplete. We can describe many storms in detail, while still working to understand long-term changes and local differences. A gauge may seem plain, but it is part of a larger human effort to listen to the sky in numbers. Rain becomes data, memory, and planning. Fresh water keeps moving through living landscapes largely because of rainfall. Most of the planet's water is salty, ocean water, and much of the fresh water is locked in ice or hidden underground. Rain delivers usable water to soils, streams, lakes, forests, farms, and cities, though not evenly and not always when needed. It feeds plants, shapes rivers, cleans some surfaces, moves minerals, and links air with earth. A single shower is brief, but rainfall across years helps build the conditions that make many ecosystems possible. It belongs to weather, climate, geology, biology, and human life at once. Rain is familiar because it touches roofs and windows. Yet it is also part of Earth's deepest cycles. In each falling drop, the planet's water is still traveling. Few things are as simple to notice as rain, and few are as large when we try to understand them. It falls past windows, gathers on leaves, darkens stone, fills rivers, wakes seeds, cools warm air, and travels through soil into hidden spaces below. A single shower may pass in minutes, but it belongs to a cycle that reaches across oceans, clouds, forests, mountains, cities, and time itself. This quiet journey has followed falling water from the first gathering of vapor inside clouds to the ways it changes the ground beneath our feet. It has shown how water can be soft and patient, yet powerful enough to shape valleys, feed wetlands, guide seasons, and leave records in trees, caves, lakes, and living landscapes. Rain is familiar because we hear it so often, but its familiar sound is only the surface of a much deeper story. Now, as the journey closes, the pattern can become simple again. Water rises, cools, falls, sinks, and returns. A gentle movement repeated across the earth. Sleep well. Good night.